Yeah, finally. I think we're online here. I'm terribly sorry about that. I don't know what happened, but I think it was YouTube has launched some new platform with their streaming, so that my stream key had actually changed. So I had to reconfigure OBS Studio.
Yeah,
Yeah,
finally.
I think
Oh,
we're online here. Oh yeah, I almost forgot to mute myself now. Yeah, everything is working. Please drop a comment in the chat if you're in there, so I know that everything is what it should be. You can hear me all right and everything. I mean, this is we're doing this like an experiment because it's new technology, which is it takes a bit of time till you get used to it. But yeah, don't give up. One should always try to learn new things. And anyway, if it should be any kind of problem with this, I am also recording at the same time, so it's gonna come online. Yeah, Oscar, great. Thank you for letting me know that it works. Perfect. Hi, Isaac. It's great. Um, that's good. Yeah, it feels a bit awkward if I don't know if anyone is able to hear me, but so that feels great. Perfect. Oh, hey, Malin. Hey, Christoph. Great. Cool. All right. So we're gonna continue from where we left off yesterday. If there are any new viewers here, it might be a good thing to watch the first lecture before this one, but it depends on your background. I think you can also have some good use of this one as well. So that's the wonder of live streaming. You can just go back and look at it at any time, any number of times that you want. So, well, let's get going here. I'm going to talk about how to do some maths in acoustics now. So this is a good use for formula for addition of sound pressure levels, and it looks like this. And if we have several sound pressures that we want to add up, several different sources. For instance, in a room like the one I'm sitting in right now, I have a little computer fan that's making a bit of noise. I have a heat pump on the wall, and then also makes a bit of noise. You have some noise from outdoors with wind and stuff. If you're in the city, you got cars and you got your neighbors and you got other activities going on. So this formula can be used to calculate what is the total sound pressure level in a room. And if you denote them by LP1, LP2, LP3, etc., and so on and so forth. So this could be like LP1 is the background noise for the ventilation, LP2 is your neighbor walking on the floor and bouncing his ball, and LP3 could be a sound stereo system. And then if you know the sound pressure level of each of these sources, you can add them up by using this formula. And that's a good tool to know. We're gonna derive some other useful rules of thumb and different stuff from this one. So I will take you on this little journey here now with this equation. So if we have equal sound pressure levels, if we have, you could say if we have one person who's screaming at the top of their lungs, and then you have 3 people or 5 people or 10 people or 100 people screaming at their top of the lungs, and they all scream with the same sound pressure level. If you want to calculate how much is the total sound pressure level when you have 1, 2, 3, 5, 10, and so on, number of sound sources, we can derive a useful little rule of thumb from this. So we used the previous formula, but the only difference I've done now is I put in here LP on every single one of them. And then we can write this one like this. That's 10 log n times 10 to the power LP over 10, like so. And then with the logarithmic rules, you can transform this a bit further to take out the n from the equation, put it in at first, and you got it like this. I write out every step of the transformation here of the equation, so we don't miss out on anything. We can take the 10 and we put it inside to get rid of 10 LP over 10 inside the parenthesis, and we end up with this 10 log n plus 10 10 log n plus logarithm of 10 to the power of LP. And then that one disappears. So this is what we're going to end up with. If we know that one sound source has, let's say, 50 dB sound pressure, then if you add 10 of those sources, you're going to end up with 50 dB plus 10 log 10. And this one is useful. Let's see what else we have here. Yeah. You can conclude it like this: the delta L. How much does the sound level change with the n number of sources? You can use this little rule of thumb for that. So n is the number of sound sources. Delta L is the difference in sound pressure level. But you have to remember that this is only valid when you have equal sound pressure level and you add several sound pressure levels. If you have different levels of LP1, LP2, LP3, then you have to use the first formula that I showed you to get it right. If we then take this and we plot it, we end up with this beautiful little graph where you have delta LP on the y-axis and you have the number of sound sources on the x-axis. And then on the first line there to the left we have one sound source and we go up to 10 sound sources. I put some red lines in here to show two useful things that I often use them when I'm out in the field doing measurements and working with sound and such. So they're good to know by heart. Now, you see, if you go from one sound source to 2 sound sources, the delta LP increases by 3 decibels. So if you have one source and you add another one just like it, you're going to get a 3 decibel increase. And then if you look at this logarithmic addition, when you go all the way up to 10 sound sources, then you get a 10 dB increase. And those are good to know. Let's see. Next slide. Now, if you have 2 different sound pressure levels, you can write it like this. Delta L equals 10 logarithm of 1 plus 10 to the power of minus L2 minus L1 over 10. And here, delta L becomes, it's the difference in sound pressure level. That is, how much louder will the total sound pressure level become with 2 sources compared to 1? You could ask that question. And this formula can help you answer that. And we say that L2 is the louder of these 2. And if you plot this one, you get this graph, where delta L on the y-axis is the difference in sound pressure level between 2 sound pressure levels, L1 and L2. So if they have the same sound that they're emitting, it's a 0 dB difference between L2 and L1. Then you have a 3 dB increase. And then when the difference between 2 sound sources gets larger and larger, delta L shrinks. So what this means is that, let's say you have a background noise in a room of 40 dB, and let's say I'm talking with the same level, 40 dB, then you will have a total increase of to 43 dBs. But if I then talk more and more and more quiet and I start to whisper, so my sound pressure level goes down from 40 to 35, then we only get a little increase in the total sound pressure level. And when the difference increases by a lot, when it's about more than 10 in this graph, you only get like 0.3, 0.4 dB increase to the total sound pressure level. So if the difference is larger than 10, it's practically negligible to the sound pressure level. And that one is also useful to know, that you know that this sound is going to be masked by this other sound because it's more than 10 dB louder than it. But if it's less than 10 dB, the 2 sound sources will have an effect on the total sound pressure level in the room. And this one is also useful to think about when we're dealing with like sound insulation in a building. If we know that a lot of sound is coming through one transmission path, like through, if you have a hole in the wall, it doesn't matter that the rest of the wall emits much less sound, because everything is going to be dominated by this big leakage in the wall, because the difference between the two sound pressures coming from the wall itself and the hole is going to be a huge difference between them. It's going to be much stronger, the sound that comes from the hole in the wall. And then that one is going to determine the total sound pressure level completely. So here are the formulas. And the one with a red square around it here, that's the basic one. That you can derive the other ones if you just know that one, you're good to go practically. And then you have also these other things that we have addition of sound sources with equal sound pressure level. You just go 10 log n, and then you will find how much louder is it going to become. Because sometimes within industry and stuff like that, you can have a certain number of machines, or maybe it's a number of fans perhaps. Then this is a really fast way to just calculate what's the total sound pressure level going to be from all these sources at once. And then finally the one which we looked at here with the addition of two different sound pressure levels. You can actually just choose the first one to get the same result. But from this, you get these useful rules of thumb. Two equal sound sources will increase the sound pressure level by 3 dB. And if the difference between two sound sources is greater than 10 dB, the quieter one is negligible. Learn these ones so you know them in your head. It's a great tool to have. Okay, now we're going to move on and start talking about how sound is measured. There are several ways of taking sound is basically something that is perceived. It's let's say this perfect example. If you're eating a sandwich, and you can measure the thickness of this sandwich to a very precise degree, but that doesn't tell you about how does it actually taste. So there are several ways of taking this perception of sound and making it into objective numbers. So I'm going to show you here some of the most useful ways of doing that. So the first one here is the weighted sound pressure level. Let's see if I can get my sound level meter here going. Yeah, seems to be running. We look at sound perhaps like this. If we have I want to go to the normal dBA. Oh, there we have it, I think. Yeah. Here. You just see there's a number when I'm talking. It's just a number. So if I talk like this on this distance, you get like, oh, there's the camera. Sorry about that. I have to move it around because I get a bit confused with all these cameras. I need to see what's going on as well. Yeah. If I'm talking into the sonometer like this, I got 80 dB perhaps on this certain distance. But if I would to give this microphone to my wife and let her talk to it instead, it will still show 80 dB or 70 or 75 on the display here. But it's going to sound completely different. And that's why we can look at it like this instead. That we have different frequencies. You see, when I'm talking here, there are a large number of bars that goes up and down here, and that's because I'm creating a lot of different frequencies with my voice when I'm talking here. So that's why when we go back to this one, we can't just use the weighted sound pressure level to get the single number, because that's like taking all these bars and compressing it into one weight. We weight them together. We might need to look at it in what we call octave bands as well. And you can also divide it into third octave bands. And perhaps if there are any musicians listening in on this, you might be familiar with this concept of octaves and third octaves is on the piano. So this is a similar thing. And then there's also FFT, Fourier transform. It's also known as a narrowband measurement, which is like a very, very high resolution analysis of a sound. You can increase the resolution of the FFT to see like individual frequencies, basically, to see, because it's like if you go from top and down on this, you have the weighted. That's a really coarse measurement. Octave band is a bit more precise, but it's still a bit rough. You go to third octave bands, you get more and more precision, and then with FFT you get a really, really good precision. But on the other hand, I mean, it depends on what you're gonna measure. I mean, if you're gonna measure the distance from my home to the city of Umeå, it makes no sense to measure it in millimeters. It's just too precise. Then perhaps kilometers is a much better way of looking at it. So you should use a resolution of your measurement that is adequate to what you want to test, because it just requires a lot of more analysis time and a lot of more horsepower in the equipment and all that. So when we look at octave bands and third octave bands, we have like 125 hertz to 250 hertz. That's one octave. 250 hertz to 500 hertz. That's the next octave. 500 hertz to 1000 hertz is the next, and so forth and so forth. Then we can take each of these octaves and split them in 3 parts, and then we get the third octave, which is 125, 160, 200, 250, 315 hertz, and so forth. And it's gonna look like this. This is just some example sound that I imagined. We have done a measurement, let's say my voice, in octave bands, and you get like these bars, a certain number of them. But by increasing the resolution to third octave bands, you get something like this. So you see, there's more detail coming out in the picture. We can get a better understanding of what's going on, because when we're designing our buildings and doing civil engineering, we need to optimize our measures that we take when we design stuff, so we don't shoot over the target. And that's why sometimes we need to be a bit more precise to focus our efforts where it really matters. Now then we have like this. If we look here at some kind of sound, octave and third octave bands, you can see 2 graphs here. So this is the same sound that we're looking at, but one of the measurements is in octave bands and the other one is in third octave bands. So it kind of looks like the third octave band values are a bit lower than the octave bands. But you can look at it like this. You see the dots, you have black squares on the octave band data, and you have round circles on the third octave band data. Now if we take this first one, the 31, it's a bit difficult to see what the graph is dealing with, but these first 3 at least, if you add those third octave bands up, 1, 2, 3, and you use the first formula I showed you, you do a logarithmic addition of those sound pressure levels, you will end up with a black square up at 80 something dB. And you can do the same thing with this one. You add those 3 third octave band values, sum them together, and you will get the octave band, and it's gonna be higher up. Because of course, if you have 3 different sound pressure levels that you take simultaneously, the sum of those 3 is gonna be more. So that's why the black squares are always above the third octave band values. So it's the same here. You add those 3, you get the black square. You add those 3. One of them is a bit over the square, but if you look carefully, you can see here that it's actually below the black one. You can also consider the other thing I was talking about earlier. I mean, you have 3 sound pressure levels here. One of them is considerably louder than the other 2. So that means that those 2 quieter ones, the 2 quieter ones a bit down there, they don't have a large effect on the total. So it's basically that one that's in the peak determines the whole octave band. Most of the energy is in that very third octave band, and there's not that much energy in the other two. So that's why it looks like so. And you can keep doing this. You add those three and you get the square, add them and you get the square, and so on and so on. So that's, if you do a measurement in third octave bands, if you configure your sonometer to third octave bands, you can always go back to octave bands from third octave bands. You just add the third octave bands and you will get the octave band value. However, you can't do it the other way around, because you can't take an octave band data and split it into three, because you have no information of how that energy was distributed within that band. Okay, let's move on here. FFT analysis, narrowband analysis, also known as. It's based on that each continuous time signal is composed of a number of sine wave signals. Now, this is a bit theoretical, but we can look at it also like this. If you have two waves, you can either get constructive interference or destructive interference. So when two equal waves hit each other, you got like wave 1 and wave 2 here, and when you add them, you're gonna get a resultant wave which is twice as high and low as the other one, because they amplify each other. You can see the same thing on water, on the sea. If two waves are coming and rolling in, and then they meet, and just when the waves meet, you get a huge wave, and then they pass on the other side. But that depends also on the phase of the wave, because if they are completely opposite to another, so that a peak hits a valley instead, so when they meet, it's gonna take this, they cancel each other, so you get destructive interference, and the resultant wave will be nothing. And this is the same technology actually that is used in, you probably tested these noise cancellation headphones. Yeah, I have it on my headset here actually. So there's a little button here so that it can, the microphones in the headset pick up the ambient sound in the room and play it back within the speaker, phase reversed. It flips it upside down by 180 degrees. So when the real sound hits your ear, and the loudspeaker here in the headphones, they emit the same sound upside down, it's gonna cancel each other out, and it's gonna become really, really quiet. And if you haven't tried these noise cancellation headphones, you really should, because it's often a wow experience. I was blown away. I mean, once you've started to use them in an airplane, it's hard to get back to not using them. And also in an office space, you know, with the open plan office, I think they're great, because you get a bit more privacy, that you can focus on your work, because it's few things are worse than to have to listen to other people talking while you are trying to do concentrated work. That's horrible. So here's a little animation. Let's see. Oh, that was a bit too fast. Superposition of waves. This is what it's gonna look like. Two waves are rolling in, and then bang, they meet, create a large one, and then they go back. This is superposition. And if you have pure tones, now what do I mean by pure tones? Let's see if I can get one rolling here. Have to, yeah, there we got that one. Tone. I'm gonna start some little here, and we get the sonometer as well. Yeah, like so. If I emit a tone, you can see here on the sonometer, and then I use this one, and I can like, this is a pure tone, whereas a complex tone is like when you play several of these tones at once, and they will combine and create a new wave, just like you can see here in this example here. You got two different frequencies. They have different wavelengths, so they're gonna look different. And when they are played simultaneously, they're gonna combine and create this new one. And then you have, if you play all frequencies at once with noise, you're gonna end up with this one, and it sounds like this. Let's see. that's noise. All frequencies at once. Now, I'm going to show you a really cool movie that I found here with an example where they actually take this concept to the extreme, that you can actually, since all sounds are composed of individual frequencies like this, you can actually create just about any kind of sound by adding a little bit of this, a little bit of that, and a little bit of those frequencies. Yeah, we're gonna look at this picture. They actually, let's see, next slide here. What they did here is that they've taken a piano, and they put small actuators on the keys of the piano, because you can consider a piano just like with this third octave band sound level meters that I showed you, with the exception that a piano, it has usually 88 keys. So you can take the audible sound spectrum and you divide it in 88 pieces, and each of these bands is going to be a key on the piano. And then you put a robot that can play these keys, and you can recreate sound. So this movie, I just love how nerdy it is and how cool it sounds. So I'm gonna play it for you now, and we'll look at it together.
Educators, politicians, social organizations. Schon erstaunlich, wie genau plötzlich die Worte der Deklaration für einen internationalen Gerichtshof gegen Umweltverbrechen verständlich werden. Wien Modern war eine von 10 kulturellen Institutionen, die um einen künstlerischen Beitrag für die Veranstaltung im Dogenpalast in Venedig gebeten wurde. Diese Botschaft mit musikalischen Mitteln hörbar zu machen, ohne auf eine simple Vertonung zurückzugreifen, das war das ehrgeizige Ziel.
We declare that we are all responsible, educators, politicians.
Ein weiterer Brückenschlag, Miro Markus, ein 9-jähriger Schüler aus Berlin, hat den Text für die Performance aufgenommen. Jugend als Hoffnungsträger der älteren Generation. Kinderstimme auf sein computergesteuertes mechanisches Klavier übertragen.
Yeah, that's really cool. I mean, how you can actually hear the piano is talking because they're playing back the speech on the keys. I mean, yeah, it was a German, but even if we don't understand German, we could understand what was going on here, I hope. So this one is beautiful. There are many other of these examples online if you look for them. I found, for instance, one that had created the Bohemian Rhapsody by Queen by just using a piano. It sounds really crazy. But when you're listening to, I mean, the whole song, the original song with drums and vocals and guitars and everything, only on one piano. And it sounds a bit crazy. It's like someone is just banging the keys like this. But your brain even hears the lyrics coming out. And it's a bit scary, but it's also very, very cool. It's so nerdy. So now I'm gonna go here and show you. This is from a commission that we had a couple of years ago, where there was a dwelling where they had complaints in the bedroom because they heard noise from an adjacent laundry room from the clothes dryer. So when the fans in that one was blowing, you got like an annoying sound in the bedroom. So here we see the difference when we have octave bands, third octave bands, and fast Fourier transform. It's with the FFT we can clearly see these peaks coming up at 50 hertz, 100 hertz, 200, 300, and now why is that? You know, the wall socket with the electricity, it's alternating current, 50 hertz. So that's the one that you can see here when the fan is rotating. It's based on the number of 50 hertz, but you get 50, 100. It's a multiple of that one. So when you have a tone a pure tone like this, it can become more annoying than if you have like a broadband noise. If you have something like that's whistling or something that is rotating, you will create tones. And those ones they have like more prominence compared to the background level, and that's why they pierce out. You can compare it if you have a white piece of paper and you take a red pencil and you just draw a line. It's gonna be super clear because the red wavelength of the red light is completely different to the background of the paper, and that's why you can really see it. And the same thing goes with sound as well. If you have a pure tone that is it stands out like this, it's going to be much more easy to hear it. So this was a good example of where I had to go and use the whole spectrum with more and more high resolution measurement technique to find the precise problem here. It's like when we acousticians are going around and trying to solve problems. This is like, with Sherlock Holmes, he has his magnifying glass and he looks for fingerprints from the criminal. And as an acoustician, this is your magnifying glass, and I'm looking for acoustic fingerprints with my sonometer to find the criminal. And usually we do a good job with this, and we can find them. And we can also use different functions on this one to really look at to find these acoustic fingerprints. If you've seen the movie with the Predator, when he shifts his heat vision goggles and he can there he can find his enemy. And yeah, it's a bit same with this. We have to use different modes to see and to find the sounds that we're looking for. And sometimes we don't really know actually what it is. So we'll move on here now, a quick little demonstration with the outer ear and the hearing organ, because now I'm going to move on a bit to the perception of sound. Now we've been talking about the objective side, the more engineering bit of it. So if we look at the outer ear, you have the pinna. Now what's the purpose of this one? It's to collect sound waves. If you do like this, so you look like Mickey Mouse, you will note that your perceived hearing changes. It's easier to hear high frequencies. It's because your hands, they will then capture the high frequency sounds and bounce them into your ear. So you can hear a little bit better in what's coming from the front when you do like so. And the function with this one is to localize sound. We are humans, we are actually really good at finding and localizing sound sources in the horizontal plane, because you get like a time difference between these two. If a sound source is on this side of my head, then the emitted sound is going to hit this ear first, and then it takes a little bit of time before it comes to the other side of the head and this ear, and you get a time difference. And from this time difference, your brain can calculate the location of the sound source. So it's quite amazing. And it can also use this because if the sound source is in front of you, you get this effect. So you get more of the high frequency content because your ears are shaped like so. Whereas if the sound source is on the back of your head, you gotta get more of this character of the sound because your ears are in the way. And then with a combination of time difference and the frequency content of the sound, your brain can analyze this and figure out where is the sound source. And it works really well. Then you have the auditory canal, which is like an S-shaped canal. It's about 30 millimeter in length, 10 millimeter in diameter, which works as a resonance canal. If you blow in a bottle in the opening and you get a tone, this means that you will get the same thing with the ears. You get certain frequencies that fit perfectly in this physical dimension, which gives this amplification, a resonance boost, up to 15 to 25 dB. You can see in the spectrum here how the sound pressure level actually gets a boost around 5,000 hertz, and then another one with around 10,000 hertz. And this is also interesting because if you consider evolution, human speech, communication, that's like the most important sound there is. And the information in the speech, the consonants, like those type of sounds, they are typically in this region where you have the resonance boost. So it's really cool how Mother Nature has designed an organism that is really tailored to hear these sounds in a good way. Whereas if you take the vowels like they are typically a bit lower in frequency. But we need the higher frequency, the consonants. That's where all the information lies. You don't have any information in the vowels. It's like when you're trying to talk to a drunk person, it can sound like there are no consonants in there, so you can't understand what they're saying. Whereas if you take a written text and you would delete all the vowels from the text, you could still understand what it says. Whereas if you do the same experiment but you remove all the consonants, it's gonna make no sense whatsoever. A bunch of vowels, and you can do it's a written form or in the auditory form. It's the same. Now I'm gonna do a little experiment here with the perceived loudness of sound. So I'm gonna play back a little swept sine. So I hope you don't have your speakers on full blast, because this can become a bit loud. But you will see like this. I've created a blue bar here that is moving on this graph, and then you can see what's going on. So let's hear it. You have the red line here is the hearing threshold, and that means that if a sound is below that red line, it's too quiet to be able to hear it, and it's easier for us to hear a quiet sound at the high frequency range because of the resonance boost in the eardrum. So now you're gonna hear it in action. When this blue bar passes by this dip where our hearing is at its most sensitive, it can almost become a bit painful because we're so good at hearing this sound. Whereas if it's in the low frequency part of the spectrum, it doesn't sound as loud, even though this is a signal that I have generated that has exactly the same amplitude all the way. The amplitude of the sound is the same, but the perception of it changes with frequency. And we can look at it like this. This is what we call phone curves, where you have the sound pressure level and the frequency here. And you can see different lines now here, that it's first like a banana like this, and then it becomes more and more straight the higher you go. Now what this means that if you take one of these red lines, the hearing threshold, the lowest one, for example, that's the level, the sound pressure level that is needed to perceive the sound level as equally loud. So if you take a 20 hertz sound and play it back at 74 dB, it looks like, that's the hearing threshold. So you need 74 dB before you even start hearing it. Whereas if you go to 1000 hertz, you're practically 0 dB and you can still hear it because your hearing is so good. Now if you increase the sound pressure level, the perceived loudness also changes. So that means that a sound at 20 hertz that is played back at 100 decibels, then we're looking at the 40 curve, the 40 phone curve. So if you have 100 decibels at 20 hertz, then you can play at about 40 decibels at 1000 hertz to perceive equal loudness of sound. And when this one goes stronger and stronger and stronger sound pressure, it becomes almost straight. So that means that at the highest sound pressure levels, you get a lower difference in the perceived. So a practical example of this could be if you play music on a really low level, it's going to be like you mess up your equalizer and you change it to one shape, and then you increase the volume on your stereo system to a very, very powerful level, that will change the EQ in your brain a bit, so it sounds differently. So that's why when a sound engineer is mixing a musical record, they have to take this into account. How loud will this music be played to my audience? Now, I think most people today probably consume music with headphones, so that's why we probably have a good idea about an average level of how loud it is played. So, of course, the sound engineer should try to replicate that. Whereas if you're mixing music that is supposed to be played back in a nightclub, it's going to be a very high sound pressure level, and then it's reasonable to use another mix of the sound to get a good balance of it. Here's a little sketch which contains now the audible sound, this green area. The audible sound is within this space, in the frequency domain and in the different sound pressure levels here. If it's below the green area, it's below the threshold of hearing, and if it's above, it's above the threshold of pain. I mean, so we're talking here about like sounds that you encounter in normal sounds, like so. It's going to be somewhere inside this one, and then we can consider music. It's typically this part of the spectrum where you have the music with all the instruments. So it's still a significant chunk of the total, because you have bass drums, you have bass guitar, you got the guitars, you got vocals, you got snare drums and tom-toms and flutes and cymbals and the voice. So it requires a whole lot of the spectrum. But when you then move on and look at human speech, you don't need as much. You typically fit in this banana-shaped little piece. That's where a normal conversation lies. Now I'm going to move on here and talk about two extremely important concepts within acoustics. And that is dBA and dBc. So we start off with dBA. This is probably the most common way of expressing sound as a number. And one could say that it's kind of a measure of how strong does something sound. How loud is the perception of this sound? Whereas if you take dBc, you also include low frequency sounds that are typically below the threshold of hearing. Now, I gave some examples yesterday, I think, with a ventilation system that is turned off, and you can feel like, oh, that was nice. What happened? It's still quiet, but it feels quiet as well, and that's probably because you had a lot of sound pressure in this red area that was produced by the ventilation system. So we also have to consider both the sounds that we actually can hear that are audible, but we also need to consider sounds that we can't hear as audible sound, but it's still going to have an effect on us. We're going to perceive it in our body like a pressure difference in the room. So dBA is here's it's a simplification. I mean, but if you know this, you're a good part of the way at least. dBA answers the question, how loud is the sound perceived? Whereas dBc is more like a measure of how loud is the sound? How much sound energy are you exposed to? But dBc is not a good measure about how loud something sounds, because like I said, if you have a lot of those low frequency sounds, it's not going to show up. The low frequency sound, they will show up, but you won't hear them. I mean, if you have dBA, that's what I mean. If you have dBA and you're going to measure the sound of the ventilation system that is turned off in the evening at 6 o'clock, you might have practically the same dBA level, but you will get a huge difference in the dBc level. So that's why we need both of them. in practice, we almost never use dB without A or C. If you look at sound requirements or measurement standards or reports or legal requirements, it's almost always with the dBA or dBc that you're gonna end up with when you're talking about installation noise or traffic noise. If there isn't the dBA or dBc, if you just have the dB, that's it doesn't tell you actually about how loud is this sound perceived. But we need all three of them, but it's very important to know about these letters. And how does this look like then? You have like two weighting curves, which is like this. You have the A curve and the C curve. So the thing is that the C curve, it follows the phone curve at a very high sound pressure level. So it's basically quite straight. There's not much weighting going on here. Whereas the A curve, it follows the hearing organ, the way we hear sound. And what this means is that a low frequency sound, if you measure it with your sound meter, a low frequency sound, and then you got like 100 dB sound pressure level at 31.5 hertz. What happens is that the meter then takes the 31.5 hertz band and it subtracts 40 decibels from it. And then it looks at the 63 hertz band and it's gonna subtract, 27 or something like that. And then it takes the 125 hertz band and it removes 17, 18. Yeah, you get the point. 250 hertz, it removes 8 from it. And then it goes through all these bands one by one and adds them up. And that's what you end up when you get the weighted sound pressure level. So if we go back to the noise complaint case here, with a bedroom where they had a clothes dryer in the laundry room adjacent to the bedroom, I have here presented the measured audio data in this room as LPZ is a blue one, and that means there is no weighting at all. It's just the levels as they were from the microphone when I measured them. That's what I got in the room. And then if you do the A weighting, dBA, you get the green ones. So then you take from that little damping curve and you remove each and every bar a corresponding manner. And when you get to 1,000, when you go to 2,000 hertz, there's something interesting going on. You can see that the green, it actually goes above. So you get a little boost. And that means because our hearing is very sensitive in this area around 2,000, 4,000. So that's why it weights them more when they do the summation of these levels to get the dBA, because they are so important for the perception of sound. And when you do the same thing with the red bars, the LPC weighted sound pressure level, it's basically straight. So you see there's not much of difference between LPZ and LPC. And that's where the weighted levels come from. Now, this part is really useful to have, because you are going to come across dBA and dBc a lot. They are used all over the place. Now we move on here. How to solve a noise problem? We can consider this as you can solve it at different distances from the source. You have something that emits noise, and you have a receiver at the other end, which could be me, for instance, sitting in my room trying to do some focused work. And you should always do it like this. Always go to the source of the problem and fix the source. That's the best and the cheapest and most effective way of solving any problem. I would say that this is probably just as valid in any domain in life. Go to the source of the problem, not the symptom. But okay, let's say that you have found the source and you've done what you can with it. Maybe it's a washing machine that is doing some centrifugal forces and vibrating. Okay, you put a better machine there which vibrates less, and you put it on some elastic layer so that it doesn't shake as much, and you've done what you can, but you're still going to produce noise. So what's the next step? Well, you have to reduce propagation. Then we have to move on to the room that the source is in, for instance, and build thicker walls to make sure that the sound cannot leave this room and go away. Or it could also be if you have a road with cars driving, producing a lot of traffic noise. You might need to build a noise barrier wall, and then we can stop the noise from propagating. That's what you do. But I mean, a better way to reduce the road noise would be to change to electric vehicles, perhaps. Then you would reduce the source of the problem. But you can't really do that. So then the next thing is to reduce propagation. Now, when you've done that part, the next one is acoustic planning. And this could be, for instance, if you have a rehearsal room where there's a band doing heavy metal music and they want to practice, and then you have an office on the next floor, and they're going to be annoyed by this music because it's so loud in there. Then you have to consider acoustic planning, like saying, the office can be used between these hours, and then from 19 in the evening, the heavy metal band can go in and take over, because then they are not there and they cannot be disturbed. Or a music room in a library and a school next to each other. I mean, it would be better to plan it in such a way that these two would be far away from each other, so they can be used independently. But if they are not, then acoustic planning is what you're left at. And you will not be able to use your building, for instance, 24/7. Because you're going to introduce some schedules that you have to follow. And that's of course, that's going to cost a lot more money and be less effective and less productive. And then the final one is like adding hearing protectors. You get a big pair of those on you and fix the problem at the source. You take off the hearing. But that's like the last resort. We should always try to get rid of it earlier in the chain. I mean, if you're disturbed by your neighbors and you complain to your landlord and they provide you with a pair of hearing protectors, here, now we solved your noise problem, you're not going to become happy. That's not a good way of doing it. So let's move on a bit. Now we're going to consider transmission paths. When you have a noise source like this, it's going to emit three types of sound. You have direct sound, reflected sound, and structure-borne sound. So we can look at them one by one. The direct sound is the airborne sound, which is the shortest path between the source and the receiver. It's like a straight line coming from the source. And then you have the reflected sound, which is airborne sound that has been reflected at least once. And here's an important difference with the direct sound. The reflected sound has always traveled further. It's a bigger distance to go up to the roof, to the ceiling and bounce back down, or bounce in the floor and come back. And that means if it has traveled a larger distance, it's gonna be more quiet. Just as if we're standing on a field 10 meters from each other and I'm talking, and then I move to 20 meters, it's gonna become more quiet because the distance has increased. Also, every time a sound is reflected, it's gonna lose a bit of energy in the reflection. But on the other hand, you get like millions and gazillions of reflected sound beams. There are an infinite number of them, and they add up. So that's why the reflected sound can still have a huge contribution to the total sound in a room. And then finally, you have the structure-borne sound, which is sound that is propagated in the structure, transmitted by vibrations. So even if you can remove the direct sound and the reflected sound from a noise source, if you forget about the structure-borne sound, you can still have a lot of trouble on your hands. So you have to get rid of that one too. Here's how we can fix the source. This is a fantastic picture that you're gonna bend a piece of metal, and you can do it in different ways. Now the one with the hammer is quite loud because it's gonna sound bang, bang, bang when you hit it. Whereas with the pliers in the second one, you fix it and then you bend. It's not gonna produce just about any sound at all. But the thing is, you have to put the same amount of energy into the metal to make it bend. But the thing is, with the hammer, it's a really, really short time. You put a lot of force into the metal in a minimum amount of time, and you do it a couple of times, like so. Whereas the other one, the force is distributed in time, so you just pour a little bit, but continuously, and that's why it becomes more quiet. So that and then impulse sounds, they are really dangerous to consider, like gunshots. If you're shooting a rifle, it's like bam, you get a huge but very, very, very short and very, very, very loud sound pressure. It comes all at once. And that means that the amplitude is also quite loud. So if you could take the gunshot and stretch it out in time for like a second, so it's going to be a slow gunshot, then it won't be nearly the same amplitude. Because you always have this energy that you need to get out. And the faster you do it, the more noise you're going to produce. Here's another example from some, perhaps it's from the mining industry or something, when they have a conveyor belt that is transporting small rocks. And then they are falling down from a large height. And it's going to go high velocity, bang, when they hit the bottom. And that's going to produce a lot of noise, of course. So what can you do here then? If you have a adjustable caliper, so you can make sure that they don't fall as not more than necessary, and you can even add some small rubber thingies that they can be like boink, 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 like this. It's going to be just a short fall. It won't build any velocity between each fall. And then it's going to be a lower force that you have that goes into each of those. So what you're doing is you're stretching out the process in time, and then the level goes down. And here's another example with resonances. This could be, for instance, the hood of your car. That's a huge metal sheet that is vibrating and emitting sound to the environment. So what you have to do with the hood of the car then to get it more quiet is to introduce damping on it, like in this figure. But I'm gonna show you here. I even found a glass. No, perhaps we can even take this camera view. Should be nice. And I'm gonna put the glass over here. Oh, it's tricky with the selfie cams, like so. And then I bang this glass. You can hear how it's ringing. It's a nice glass, so you get a nice tone for a long time. And then we just add some damping. It's gone. By touching it, it cannot vibrate freely anymore. So that is a very good way of reducing sound too. And here's some examples on how you can reduce propagation. Now, if you have free propagation, it's going to be like the first image here. You got direct sound, reflected sound, and structure-borne sound. All three components coming at this poor fella at once. And then the second picture, they have added vibration insulation to remove the structure-borne sound. And this is really important. Very important. It's easy to forget, so don't do that. But you see, then one of the components is gone. And the next step would be to try to get rid of the reflected sound. And you could do that by adding sound absorbers in the ceiling, for instance, because then the sound that would have been reflected in the hard ceiling, instead it's going to be converted into heat energy. and it's not going to come down at you anymore. So now you basically only have the direct sound to consider, and that one you can stop it with a sound screen, like in the final one. You see there how he becomes really happy, this guy, because it's reflected away, and it's actually the direct sound now is reflected and going up into the ceiling where it is absorbed. So a combination of measures is the best way of attacking a noise problem. Do them all. You encapsulate your noisy machine with absorbers inside and a sealed box, and it's standing on some kind of springs or elastic interlayer so that the structure-borne sound cannot be propagated. And then the best one would be to separate the noise source and the noise disturbed in separate rooms of the building, because that one, when you build it inside a little cavity with a little box, you can't operate the machine in the as easily. Whereas in the second one, you could go in there and do some maintenance work on the machine much more easy, and then you handle the sound problem with a completely different space, a different room. So always fix the problem at the source first and at the receiver last. Very, very important. And also here's when are you supposed to fix a problem. Like if you look at the process of a civil engineering project, for instance, you have the cost on the y-axis and you have acoustic quality on the x-axis. And then you have different stages in the project here. The first one is planning, the second one is construction, and when they start to sign the deals and buy stuff for the building. The third one is when they have started to construct the building, raise it, and it's starting to take shape. And the final one there is when the tenants have moved in and started to use the building. And then the cost becomes more extreme the later you try to fix it. So we, as a civil engineer, if we can get the consultants involved as soon as possible and to get the big building blocks of the building sorted out before, it's going to be so much more money we can save, and the solution is going to be so much better, and the perceived sound quality, everything increases when you do it like that. Because it's much cheaper to change a couple of lines on a CAD drawing than to start to evacuate tenants, put them in a hotel, move their furniture to some storage, go in and do... First you have to tear stuff down and do reconstruction work, put it back, and then move their furniture back, get the tenants in there, and they probably need to get some economic compensation as well. And if we did this in a building which had extremely high sound requirements, well, of course, it scales even more. That's why you get this acoustic quality exponential growth. Whereas if it's not a sensitive, if it's just a barrack, I mean, then it's not that big of a deal to go in and do corrective measures. Whereas if it's a dwelling where people have their home, that's a much bigger deal. I think we can take a little rest for our brains here for a couple of minutes. We'll give it a 5-minute break, and I will continue. I'll leave the live stream running, and you can catch your breath. And I'll talk to you guys soon again. Okay, 5 minutes has passed, so we move on now with the lecture here. I just remember a little example while I was catching my breath here regarding the dBA sound pressure levels that I want to show you. So if we go to the sound pressure level meter view again, I have this little app on my phone. So with this one I can create different kinds of noise. So if we do, let's see, white noise first. Then you can see the bars moving here on the graph. I'm gonna go so I have dBA. There we have it. Now if I go from dBA and I switch to a more low frequency noise, you can see on the bars here how the spectrum shifts, it tilts more and less low frequency content. And if we then take a look at the dBA value, and that's the one that you have on top of the screen there, you see LAFSPL. If I go from the one here, the white noise, this one is perceived as loud, and it's when I go to the more and more low frequencies, it's less and less harsh on your ears. You can see how the dBA level changes also when the frequency content changes of the noise. Now if we take a look at the, it went down. It was like 74-ish, and then it went down to like 69 with the most low frequency. If we then change the sound level meter to take a look at the dBc level now, C-weighted sound level, the one that also considers the lower frequencies without weighting them down. So this is what it's going to look like. 77 dBc. You can see here how the dBc level increases clearly when we increase the low frequency content of the sound. Whereas with the dBA, it was the other way around. So I hope that made sense, this little demonstration. Now we're gonna move on here. I'm gonna take a look at different wave types, how sound is propagated. And there are three basic types of wave propagation here. Spherical sound wave, cylindrical sound wave, and plane sound wave. And we're going to look at them one by one now. The first one is a spherical sound wave, which is created by a so-called point source. Now, what is a point? The definition of a point is that it is so small that it has no dimension. It doesn't have a length, width, or height. It does not have a front or a back side. A sound source that is small in relation to the wavelength, that is a point, thus does not have a direction and therefore radiates sound in all directions. A point source. And then we need to consider when does this occur? What does small and large in relation to mean in practice? Well, you could say about the sound source works as a point source if it is small, about 1/10 of the size in relation to the wavelength. So here we have a little example question. Will a 4-inch loudspeaker behave as a point source if it emits sounds of the following frequencies: 34, 340, 3400, and 13,600 hertz? So we can calculate them and check it out. Let's trust my old trustworthy Casio calculator. I've been using this one for more than 20 years now and still going strong. And here's what I mean with a this is a 4-inch loudspeaker. The woofer membrane here, it's precisely 4 inches. Will this loudspeaker behave as a point source if I transmit the sound of those frequencies that I show here? So we start to calculate. And then I had this little memory triangle I told you about last lecture, which it comes into good use here. So the first one, 34 hertz, we know the frequency, and we know c, the propagation velocity, is 343 meters per second in air. So here we can take 343 and we put it in c, and then we can just cover lambda on that little triangle, because that's the one that we want to know about. We have the triangle like so, and we want to know lambda here. So I do like this. C divided by F will give me lambda. It's a very useful little rule. So 343 divided by the frequency F, 34 hertz, and we get 10 meters. So the wavelength of the first one is 10 meters, and the loudspeaker is 4-inch, which is 10 centimeters. So that's, of course, when you take a little look at this little fella, it's gonna emit a 10 meter wavelength. It's gonna be very, very small. So that one is just a point source in compared to 34 hertz. Now it can't emit those kind of low frequencies because you're gonna probably need a big subwoofer to do it. But it's just a theoretical example here. We do the next one then. 340 hertz. 343 divided by the frequency, and then you will get, oh, where's the camera? 1 meter. So the wavelength is 1 meter on the loudspeaker, which is 10 centimeters. So then we are actually now precisely at the point here with the relationship of 1/10 in relation to the wavelength. So here at 340 hertz, this loudspeaker is going to start to stop. It still is a point source, but we're at the limit, because now the wavelength is shrinking. The higher we go in frequency, the shorter the wavelength will become. So that means also in relative to that, the loudspeaker is growing in size compared to the sound. So there we are at the limit. So 340 hertz, it's still a point source, just. And then we do the same thing. We go 343 meters per second divided by 3,400 hertz, and we get 0.1 meters. Now it's the same. A 10 centimeter loudspeaker is emitting a sound which has a wavelength of 10 centimeters. This condition is not fulfilled then. Now it's not a point source, and now it's not a point source anymore. It's starting to behave as with directivity, that the sound has a direction. It has a clear front and a back side. And then the final one, we go 343 meters per second divided by 13,600, bam. And then you get a wavelength of 2.5 centimeters. Now the loudspeaker is starting to become very, very large in relation to the sound, because 2.5, that's my thumb is precisely 2.5, and you see it's a large woofer on the speaker compared to my thumb. So now it's much more directional, the speaker. I'm gonna see if I can do another example here also, which is quite useful. We go back to the little app I have here, and I'm gonna play back some sound. Yeah, we have that one. And this one is actually, we can perhaps go to the sonometer view, perhaps is a good one, like so. yeah, you see 440 hertz. We go lower in frequency, 110. I don't know. Not sure how low we can go on this one. About, yeah, it's on now. It's 91.3 hertz in the signal generator. So then this little speaker is a little Bose Bluetooth speaker that I have. It's quite small, and if we're emitting 91 hertz, it's gonna be we can go perhaps. Come in. Yeah, the microphone. I don't know why it does that. It's like it disconnects and then it reconnects. Luckily, there's a little click, so I know when it's gone out. But now I see the audio is back in. So, join the Texas Instruments team instead. Yeah, there are two teams battling there. I'm a Casio guy, as you can imagine. My wife is a Texas fanatic. Let's see. Here's the demonstration now. Low frequency sound. And this is like a point source now. So even if I rotate the loudspeaker, there's hardly any difference in perception of sound from this one, because it's emitting the sound in all directions at once. This is like a light bulb that emitting light in all directions. But if we crank up the frequency, so now it's gonna be this high-pitched annoying sound instead. I don't know if the microphone can pick this up, but if it does, it's probably gonna sound quite unpleasant for you. And we'll see how this works. I haven't tried this on a live stream before, but when I oh, don't swear. It sounds really horrible when I'm directing it in another direction away from me. The sound is going out. This is the face of the speaker, so it's going out. And this is like pointing a laser beam pointer in your eyes. Oh, it sounds horrible. Really, really bad. Make it stop, please. Jesus Christ. Oh, there we have it. So that's a good demonstration on how this very same sound source, when we emit different frequencies from it, it becomes more and more directional. So the first one is like a light bulb, is going all directions as once, and then when I crank up the frequency, it becomes more and more like a laser pointer, and then we get the laser right into your eye. It's gonna be very unpleasant. And the same is valid for your ears as well. Now we have the next one here. Cylindrical sound wave, a line source. And that's a sound source works as a line source if it is long in relation to the wavelength. Now this can happen where you have a sound source where one of its dimension, length, width or height, is a lot larger than the other two dimensions. Then you can have something that produces a cylindrical wave propagation. And you can see here on these little figures that I added that it's like cylindrical shells that are growing. Like if you have a pipe that is emitting sound from its whole area, then you're gonna get like a cylindrical wave propagation from it. You could produce this when you have, consider you have many point sources that are close to each other, one after another, like this, like a necklace with the pearls, and then you have many point sources, and when they produce sound, they will create cylindrical sound waves. Now, this is where I usually ask my classroom, now, do you know of some kind of source that could be a line source? But I'm going to show you here some pictures now. I don't know, you can think about it like for a little while here and see if you come up with something. Where do we have a lot of point sources that create sound in a long line and emits at once? I have some proper examples here, and you will see. Well, here this one is like the perfect example of a line source. the train. Look at the wheels of the train. They go round and round and round, and it's a very, very long train, this. And you have a lot of wheels on it. And every single wheel on this train acts like a point source. But when they are placed in this manner, next to each other, line array, correct. It's actually one of the examples that I'm going to show soon. And when they radiate sound at once, this will be cylindrical wave propagation coming out from the train in all directions. And here's another one. A heavily trafficked highway. You see how many cars here. This is 1,000 sound sources, and they are all in the same. They are aligned, producing sound, and it creates this cylindrical wave propagation. So this is another form of line source. And then we have in the chat there, Isaac, great. A line array speaker. You've probably all seen this if you've ever been to a bigger concert. The speakers are placed like this. And this is a great way to throw the sound at a further distance. That's why they do it like this. Because you have all these PA speakers on the left and right side of the stage. And by placing them on top of each other like this, you will have cylindrical radiation from the stage to the audience. And the thing is with the line array, the line sources, is that they are better at distance. You will lose less energy with the distance compared to a point source. Because if you had a point source, if you just had one big loudspeaker on each side of the stage, then you would have to crank up the volume a lot more so that the guys at the furthest end in the audience would still have an acceptable sound pressure. But then the drawback is that the poor guys at the front is gonna get their ears destroyed because the sound is so loud. But by going to a line array loudspeaker like this, it's gonna be quieter close to the stage, and you will still have proper sound level at the furthest end of the concert. Now, then finally we have the plane sound wave. And that's something that happens when when the sound source is very large in relation to the wavelength, where you have a plane where the wave is in the same phase all across the plane all at once. It's like a big sound speaker membrane that is moving together. And I like this little picture with the golf balls, where you could consider it as many point sources. Point source and ball, it's pores. You never know what happens in a live stream. You have a lot of point sources in a box like this. And when they are emitting sound all at once, in phase, synchronized with each other, you can create a plane sound wave that is coming right out from this thing. So here are some of the characteristics of that one. If the emitted wavelength is short in relation to the sound source, the sound is more directed. A loudspeaker can behave somewhat as a plane wave source when it emits a high frequency sound, as a tweeter, for instance. I mean, with a tweeter, I mean this. You've all seen a loudspeaker, and then you have the woofer here, and you have the tweeter. This one takes care of the low frequencies. This one takes care of the high frequencies. So if you have a loudspeaker at home and you turn on some music, and you can move around and go and listen to how does it sound at different locations. You will find that the it's more crisp sound when you're right in front of the tweeter. It's like you could consider it like a laser beam is coming out from this one straight out into the room. So when you want to do a proper speaker setup like this one here, for instance, I have speakers on the side of my monitors like this, and then I point them at my ears so that they have one ear each. I mean, it's not the perfect setup this, but it's quite good. Oh, sorry, that's the one. So it doesn't mean that you need to have a sound source that is like 100 meters in length or width. It's the size relative to the wavelength that you're emitting. That's what's important here. Because you also have ultrasonic sensors, like the parking assistance on your car. You know those things at the front and the back, they're like a coin in size. They're actually small loudspeakers that emit sound that is going to the wall of the next of the garage or the next car. They reflect it and bounce back, and they are picked up by a little microphone, and then it will know the time difference. How long did this reflection take? And it can figure out how many meters do we have left before it says crash. Now the directivity of the sound source is determined by the frequency thus. I found this little example of a plane wave source, which I find a bit funny because I'm a death metal guitar player. But then we have this guy, Yngwie Malmsteen. He has this saying that there are two man-made objects that you can see from space, and one is the Great Wall of China, and the other one is Yngwie Malmsteen's Wall of Marshalls. So this is the one. And you know, an electric guitar, when you play it, it has a quite of a it's a higher frequency sound, a bit more harsh on your ears. If you're standing straight in front of an electric guitar, distorted guitar, and you do like that, it's gonna be quite strong sound. Now when you do like Yngwie here, and you put a huge number of big cabinets like this, this one will be insanely focused to the front. So with this contraption, you can throw the sound an insane distance, really long way. I mean, you could probably find stuff like this also when you have, if you want to shoot propaganda over the border to your enemy, maybe like in North Korea, South Korea, perhaps you can find speaker sets like this, because they can literally go like kilometers when you create something like this. But for us normal people, it's more common with this type of things when you use the high directed sound sources to use them like for parking sensors, ultrasonic. And you see this example here also, that they tried two different ultrasonic sensors with 40 kilohertz and 48 kilohertz. And when the 40 kilohertz, it's not as direct, the directivity is lower, and then it actually goes and it bounces in the ground and it comes back. And it's gonna say, oh, you're about to crash into the next car. Well, what do you mean? It's far away. But if you increase the frequency of the sensor, then it becomes more like a laser beam, and then you get a more precise measurement. Now we move on to free field sound propagation. And with free field, I mean when sound is propagated somewhere where you have zero reflections. There are no surfaces around you that it can be reflected on. And one example of this that I personally experienced was when I took my snowmobile and I drove it far out on the ice in the winter, where it had dumped a lot of snow, so it was porous snow everywhere, thick layer. And then I went out on the ice, nothing around me. And then I turned off the engine and I was struck by the silence, because that's just about the most quiet I've ever been, at least outdoors, because there were nothing that could reflect sound except myself and the snowmobile, of course, but that's not that much. So when you do like this, when you clap your hands, it just sounds like boop, it's a little infinitely short smack, and then it's gone. Because if you clap your hands right now where you're listening to this, you are close to surfaces all around you, and you will get reflections, and then you will it's elongated over time, so the clap comes back at not all at once like it does when you remove all the reflections, so you get something else. But now we're going to talk first about free field sound propagation, because you always have free field sound propagation also inside a room in a building, because close to a source, let's say if my little AirPods here, if this is a sound source, you will have free field sound propagation at least for a radius of like 60 centimeters, because if I hold it like this, there are no surfaces close to it, and then you have free field sound propagation. But then when it starts to hit my desk and the wall and the ceiling and stuff, then you're moving on into the next domain. But first we deal with the free field propagation. And it looks like this when you want to calculate it from a point source. You have LP, level pressure, that is sound pressure level, and then you have LW, which is the work W, and L level. So it's the sound power level, how much power is emitted from this sound source, just as how much power do you have in your radiator, or how much power do you have in a light bulb. That one is independent of the surroundings. And then you have 10 times the logarithm of 1 over 4 pi radius squared. And that one comes from that the energy is distributed over a spherical surface. That's why you have the formula for a sphere there. And if you know the sound power level, which can be measured in a laboratory, for instance, of a product or a machine or something that, and you want to calculate what's the sound pressure level going to be inside this room if we install this equipment, and then you can calculate it with formulas such as this one to get it at a certain distance from the source, on the condition that you have zero reflections. We'll deal with them a bit later. So here's an explanation of the formula. You have the sound pressure level at a distance r, that's the first term. Then you have the sound power of the source. You have the 10, which is the deci in decibel, just like kilometer or milliliter, but here you have deci for decibel because it gives us the most proper size of the terms with integer values. And then you have the area of a sphere, point source. And then you have this red expression here, which determines how many dB has the sound been attenuated at a given distance r from the source. The sound power is distributed over a growing sphere. Now we want to know, how does the sound pressure level change when the distance is doubled? Like if you go from 1 meter to 2 meter, or 2 meter to 4, 4 to 8, 8 to 16, and so on and so forth. So we're going to do a quick calculation about that. So we define the terms like this. First you have the sound pressure level at a distance r, which is LR. And then you have the sound pressure level at twice the distance r, which is L2R. The difference between these two are LR minus L2R. And of course LR is the louder one because that's the shorter distance. 2R is twice the distance, so it's going to be much more quiet. So LR minus L2R. Then we insert these variables into this formula and see what happens when we double the distance. LR minus L2R gives us this one, and I've printed out every step of the equation now, so you can when you're looking at it, you can also pause it and follow it in your own pace if you want to. You got the sound power level. The sound power level is the same in both cases because we're dealing with the same sound source, just we only change the distance here. So first we have the sphere with the radius r, and then we had another sphere with the radius 2r, and then we subtract those one from each other like so. And that will give us this expression, because the sound power level now, you see it's a minus sign there, so it disappears, it's cancelled, and we're left with the logarithmic terms now only. Now what can we do with those? Well, you can use the logarithmic rules and put them together like so on a common denominator. So you have 10 log also, and then 1 over 4 pi r squared divided by another fraction, which is 1 over 4 pi 2 radius squared. And that one we can then rearrange because the ones they cancel out, so you can write it like so: 4 pi times 2 radius squared divided by 4 pi 1 radius squared. And now 4 pi cancels out both on the top and the bottom, and then you're left with that one, which also cancels out a bit more, because 2 squared is 4, and then you have r squared over r squared, and those cancel, and you got 10 logarithm of 4, which is going to give you something like 10 times 0.602, which is approximately 6. So this means that you get 6 dB lower sound pressure level when the distance is doubled. And the beautiful thing here is this is valid if you go from 1 meter to 2 meter. It's valid if you go from 2 to 4, 4 to 8, or if you go from 30 to 60 or 40 to 80. You always have this rule of halving, that rule of doubling the distance when you're dealing with point sources. Sound pressure level is attenuated by 6 dB for every doubling of distance in free field for a point source. And we can plot this one, and it's gonna look like this: free field propagation. So I got a logarithmic distance scale on the x-axis here, and then you get a nice straight line here that diminishes. So that means that if I'm talking and you're listening at a distance of 10 meters, it's going to be 20 dB more quiet at 10 meters compared to if you were standing at 1 meter distance and talking to me. Now we're going to deal a bit with the effect of surfaces. So we can check at the floor first. So you have a sound source, like you have this little Bose speaker, and it's emitting low frequency sounds, we say, in all directions. What happens if you put this one on the floor, bang, on a surface? You have the same sound power level in this one all the time, but now the energy is not distributed over a sphere anymore. It's distributed over a half sphere. So what happens here is that all the energy that was supposed to go down is now reflected and coming back up at you. So you will see a reflection. And if you could see sound, it would look similar to this one. You get a reflection. And this looks like two sources. So it's going to sound a bit louder. Here's another beautiful picture of the moon where you have reflections. This is completely analogous to sound also. So when you have a sound source, it's going to be reflected in different ways depending on the characteristics of the surface. So you see the water surface is not perfectly flat. It's a bit irregular. And that's why it's a bit distorted, the reflections from the moon. But I want to show you this really cool device, which is called an acoustic camera, which is basically a big dish with a lot of microphones all over it. And these microphones, when a sound wave is coming from a source, all the different microphones, it's going to be a different distance between the source and the receiver. So they're not coming at once. And they will have differences in between. And then you have a computer program there which can analyze the signal from all these microphones and let it work its magic. And with this, you can actually create a picture and see the sound, what it looks like. And I think this is beautiful. At first you have this motorcycle that is running on idle, and then you look at it, you can see clearly where is the sound coming from. It's coming clearly from the engine, but mostly from the exhaust system there, from the pipe. And then you have the silencer, and then it's the opening at the back. Perhaps there is no red color at the back of the silencer. Could be because it's like pointed out from the silencer. So if you move the camera to the rear of the microphone of the motorcycle, you could hear. You would get a stronger red indication. But the lower pictures here are also great. You see the train. You have every wheel of the train lights up like a strong red color. And then you have this thing that takes the electricity from the wires to the train, which is scratching and also creating a lot of sound. So that's what you see here from the moving train. Then you have the wind power plant here. You have each of the blades of the propeller, which is like it's creating a lot of turbulence when it's moving through the air. So then you have like 3 sound sources there, and then you have the thing in the middle, the generator, which also is creating sound as it rotates. And then we have the airplane, which is my personal favorite, because here it actually looks like the picture of the moon that I showed you. You see the jet engine is running, and it's lighting up in purple. It's extremely strong sound pressure. And then the landing strip on an airport, it's like the tarmac. It's flat, it's very hard, so you will get a really good reflection from it as well. So there you see the reflection of the jet engine of the aircraft. You can see the reflection of it in the tarmac. You can't see it with your eyes, but you can see it with your ears. If you have this acoustic camera, you can actually see it when with your eyes as well. And then finally, you have someone's playing the violin, where you can also see where the sound is created from the violin. It's from the top, and that is vibrating like a loudspeaker membrane, primarily. Now you can also put the sound source in a corner. And here's a little thing I recommend you try this one out for yourself back home. What happens if you have, perhaps you have a little loudspeaker, Bluetooth speaker like this. That's a good way of testing it. And try to place it in free field. You put it on the floor, you put it against the wall, you put it in a corner, and see what happens with the sound. The best room to try this if you're in an apartment is to go into your bathroom. Perhaps in the shower you have hard surfaces. There it's going to be very, very clear. You can even do it if you just put on some music on your smartphone. It's a bit weaker in the low frequencies, but it's still going to work. You put it on the floor and in a corner and in a free field, and see how does the character change. I think you will find that it becomes louder. But really strong boost when you put it towards surfaces, and especially in a corner. Because what happens in a corner, consider this to be 3 optical mirrors that are standing like this. And then you put an apple in the corner with these 3. How many apples are you going to see? Well, you will see, this is 1/8 of a sphere. So you're actually going to see 1, 2, 3, 4, 5, 6, 7, 8 apples when you put them in a corner with mirrors around them. And the same goes for a sound source, if it is a point source. Because if you put a directed source, like when I did the high pitch sound from this one, that one is like a laser beam. I mean, if you put a laser beam pointer and you put it towards a mirror, you will still only see one laser beam because it's directivity. But when you have a point source which is omnidirectional, then you will see 8 apples in the mirrors. So try this one out with some loudspeaker of yours. It's a really powerful demonstration. I usually do it in a classroom, but I tried it out here before. I can't do it on the live stream. Maybe I'll try to figure something out in the future, but you can do it for yourselves if you have a little Bluetooth speaker or a good cell phone with speakers. So do it and see what you find out. So how does this affect what's going on? How does the floor, what does it do with the propagation? Now everything that goes into the floor is reflected back, so the energy is distributed over a half sphere, and the area of a half sphere is like this: 4 pi radius squared divided by 2. So we get 2 pi radius squared, which makes the formula like that. It's the same formula, but I just shifted to a half sphere instead. And we'll do the calculation, doubling of distance when the source is on a surface. Because it can be like that. You think that maybe if I put it against a surface, it's going to be better at throwing sound at large distance. Well, it's not going to be better at throwing at distance. What will happen is that you will get more sound that is coming at you, but you will still lose the same every time you double the distance. And I'm going to prove it to you here. So you put in the formula like this. You have the distance r and double r. And then you subtract them from each other. You get this expression instead. Sound power level, it cancels out. We use the logarithmic rules to write them into the same, and then you have the common denominator, and the ones cancel out, and you get this one. And then you have the 2 pi's that cancel out, and you're left with 2 radius squared over radius squared. And they cancel out, everything except the 4 cancels out. So you get 10 log 4. And that was the same as before. So even if you put a point source towards a wall or a floor or a corner, you will end up with the same thing. But you will get more sound back at you, because it's like you get more of the sources if you look at it as mirrors. That's a really good way. Actually, when I went to do some grocery shopping some year ago. I was at Ica Maxi in Umeå, which is a big food store, a huge one with a big facade. And we have the airport, which is rather close to the city in Umeå. And when I was walking to my car, I could clearly hear an airplane that was taking off. But it was coming from the other direction, not from the airport. And I was, wait a minute, what's going on here? It's a facade. So I got the airplane reflection in the facade, and then it bounced back at me because the plane was taking off, and I couldn't really see the plane, but the reflection hit me really strongly. So that was an interesting observation. Those are the type of things that I mean that an acoustician. We see the world with our ears in a different way than a normal person, because I always go around and listen. Which surfaces are reflecting this sound and that sound, and I practice my brain to start to see. I like to see at sound, like if I had an acoustic camera built into my head. That you can kind of do that when you do thousands of measurements. You listen critically and you run around with your acoustic magnifying glass and searching for the fingerprints. And I mean, it's a great exercise for your brain. So this is where you end up with. No matter how many surfaces you've got, if it's a point source, it's always attenuated by 6 dB for each doubling of distance. You can also come across something called like a directivity factor or a Q factor. And the purpose of this Q factor is to consider the placement of the source. If it's free field, if it's on a floor, if it's on a wall or in a corner, etc. I mean, this is highly relevant if you, for instance, if you're going to do some calculation on a big fan equipment that is going to be mounted to a wall, and then you want to know what the sound pressure is going to be like in some adjacent dwelling which is nearby. Well, then you have to consider the effect of the wall, because you're going to actually be dealing with kind of two, one real source and one virtual sound source that's going to send the sound towards you. So this is stuff you need to consider then if you're calculating with sources that are placed toward surfaces, which they often are. Consider what's going on in a building. If you have a ventilation opening in the ceiling where the air comes, where it's sucked out or pulled into the room or whatever, it's in the ceiling. That means it's got a big surface there. So if it's acting like a point source, you get more. It gets a free boost. Whereas if you would solve the ventilation, like if you could pull a pipe that comes down into the room, so it's like a free opening, then it would become a point source instead. But if it's in the ceiling, it's gonna be you have this Q effect. Here's a picture of an omnidirectional loudspeaker. This is one that I'm using when I do my sound measurements in the field. And this one is like a big ball, which with several speaker elements all around it in every direction. And you can see here, this is a measurement that was made in a laboratory when they put this one on a rotating table, and you have like extreme sound absorption on all surfaces, so there are no reflections. And then you rotate the speaker 360 degrees, and then you just measure what sound do we have at different frequencies while it is rotating. And then you'll see here that at 100 Hertz, long wavelength, low frequency, small sound source in relation to wavelength, it's omnidirectional. It's basically the same, the whole revolution. And it's the same for 315 Hertz. It's a omnidirectional. 1 kilohertz, it's still omnidirectional here. But then when you go up to 3115 Hertz there, the final one, now it starts to look and resemble kind of like a flower. And that is because the individual speaker elements is starting to become more and more directional. And then you cannot produce omnidirectional sound with this sound source above a certain frequency. And you could solve that by building a new, from a tennis ball, a really small one, with a lot of small loudspeakers. Then you could continue with an omnidirectional sound source instead. It's really easy to have a omnidirectional sound source for very low frequencies. All you need is a subwoofer. Like if you have a home cinema and you have this subwoofer speaker, you can't really have a direction on the sound from that one. If it's pointing at you or if it's pointing to the side, it doesn't matter because it's a point source. It's emitting sound with wavelengths of meters. And the subwoofer is maybe 8-inch, 10-inch, 12-inch. It's very small in relation to the wavelength. So it doesn't matter that much in which direction it's pointing. It is important where you place it in the room, don't get me wrong here, because the distance to the subwoofer is critical if you have several speakers. But that's now I'm drifting out on a tangent here. That's a different course, loudspeaker theory. Now we're going to do the same experiment here with cylindrical and plane wave propagation. How much is the sound attenuated with these types of waves? So at first you have an area of a cylinder, which is 2 pi radius times the height of the cylinder plus 2 pi r squared. So you need to take the surface area of the cylinder, and you also need to consider the top and the bottom. Now, if you were dealing with the cylindrical wave propagation here, like the train, you could say that the height of the train, if it's standing on top, it's going to be a really big surface area compared to the little front of the train or the back of the train. So if we have the energy like this, it's distributed over a cylinder, and the area of an infinite cylinder is going to become 2 pi radius times the height. Because the top and the bottom of the cylinder are negligible, because they are very small in comparison to the length. And then the formula becomes like this. It's the same one as before, but we put in the formula here for the cylinder walls, basically. And we put it in the old trusty formula once again, and it doubled the distance with cylindrical propagation. And you have the same. You can, if you want to look at it, you just pause the video and look at it later. You have the sound power level, and you have those expressions: radius, double radius. The sound power level, it cancels out, and you're left with this. You use the logarithmic rules to put them together inside one, like so. And you have 1 over 2 pi radius. The ones and the ones, they cancel out, and you can write it like this instead. Now we have many parameters here or variables that you can cancel out. 2 pi h is both up and down, so let's get rid of those. And we can get rid of the r also, and the 2's. So you're left with 10. You're left with 10 logarithm of 2, which is actually 3 instead. So here you have the key difference between a point source and a line source. You get 3 decibels lower sound pressure level when the distance is doubled for a line source compared to a point source. Sound power level is the sound pressure level. I wrote the wrong thing here when I was translating my slides. It should said the sound pressure level is attenuated by 3 dB for each doubling of distance for a line source. The sound power level is always the same. The radiator has a given power level, and the light bulb is a given power level. It's not that one that I'm talking about here. Every time you double the distance, the sound pressure level is reduced by 3 dB for a line source. In comparison, the point source is attenuated by 6 dB. And here's the example with the line array speakers at the concert. Because if you attenuate by 6 dB, it falls off more quickly. Whereas if you attenuate by -3, it's a slower decline. And that means that you can, if the line shifts like this, you can get it down, and you will still have proper sound at the furthest point in the audience. So thus, a line source is better at transmitting sound at larger distances. But this is also something that we need to consider in civil engineering when we're dealing with railroads and roads, because they are good transmitters of sound at large distances. Very important to remember that. And now finally we have the plane wave propagation. So the energy is propagated over a plane. How much is the sound pressure level attenuated for an ideal plane wave, theoretically? Well, the energy is distributed over a plane, And the area of an infinite plane would be like b times h, the width. Oh, it's in Swedish. Breadth. Width times the height of the plane, which would be make the formula like that. I mean, and then when we double the distance, you get the same expression in both terms because it's not dependent on the distance at all. So you're left with 0. You get 0 dB lower sound pressure level when the distance is doubled. In theory, the sound pressure level is attenuated by 0 dB for each doubling of distance, theoretically. A plane wave source is therefore extremely good at transmitting sound over large distances, and the sound thus has a very high directivity. Now the clock, I see I've passed a bit over 12 o'clock here, so I mean, considering the schedule of the course, I'm just gonna go ahead here because we're live streaming and you can go and catch up later if you need to take a little break. But I think I'm just gonna go now. I'm at full steam, and we'll see where I find a good place to stop here. So that's I hope that's not a problem with you. But you can take a break here if you want to and come back later and have some lunch. But anyway, here are some examples from a commission I did a couple of years ago. We were gonna check out the noise from a grocery store where they had a condenser from the cooling equipment on the roof of the grocery store. And here's a satellite photo of the situation. You see, you have the grocery store in the middle, and you have this thing with a white on the roof of the building, and then you have different dwelling houses around it, like so. Now we want to know how much sound is gonna come to the facade of the adjacent dwellings, and how do we measure it? So this is we go a bit closer so you see. It's like 4 fans here on top of the building. And we zoom in a bit closer. Here's what I did. I did measurements at different points, at different distances. And I could barely reach 16 meters without falling over the edge of the building to the ground. So this was perfect. Like 1, 2, 4, 8, and 16 meters. I did measurements in both directions, both in the X and the Y direction here. And by looking at these measurements, I could do some extrapolation and figure out what was going on. So we saw that, like here, you see, if we back up perhaps, this is both like a line source and a point source, depending on from which way you are looking at it. If you're looking at it from the side, it's like, you know, in those old sailing line ships with Admiral Nelson and those guys, when they had the cannons, when they say that we fire a broadside, you have all the cannons lined up on the ship, and it's like, bam, you got a huge firepower. Whereas to the front and the back of the ship, I don't know the nautical terms now, so so don't hate on me for that. I don't remember them. But anyhow, you can basically just fit 1 or 2 cannons in the front and 1 and 2 in the back. So you get not as much firepower in those directions. And it's the same with this sound source here. You get a line source in one direction, and you get a point source in the other. And then you can do some extrapolation from the measurements. And you could see that you had like 3 dB attenuation when you're going on the broadside. But when you're going from the front or the back, you had more like 6 dB attenuation every doubling of distance. And by using that, we could extrapolate these values and see what we will end up with here at the different buildings. And I did some like average of both of them. It's going to be like a vector that is going in a different direction compared to the other two. So it's like a quick and dirty measurement, but it was just to get an indication of what's going on here. But I thought it was a perfect example here where you could see something that is both a point source and a line source at once. All right, now I'm gonna just take a look at where I am in my lecture. I think this could actually be a really good place to end the lecture for today. So really glad you could join us here. That's I think this is a great way of doing education. I love it, and we're learning stuff every day. There are some issues here and there, but we'll solve them. It's no big deal. We have to try to use this new technology. And I actually, when I started to do this education, I was looking at PewDiePie like a couple of years ago, and I was like, wait a minute, I could do this, but within my acoustics course. And I think it works really nice, because now when we get these lectures out there and they are recorded, we can take the time that we save here and use them for other learning activities while sharing them with the world, which I think is so awesome. I've already got feedback from people that have watched the last lecture. They drop me an email and they say, yeah, think about that. What if you do this? And amazing. So please leave me some feedback here in a comment, or you do it in an email or on social media, wherever. Give me a phone call, whatever, and let me know one thing that you think was good with this lecture, and one thing that you wish that I do next time. And I'll talk to you again next week. I think it was on... I'll drop it in the comments or something where you can find the next lecture. There is a playlist where I add them, and they will keep showing up. So, have a nice day.